Thank you for your introduction. Hello everyone, I'm Zhang from Tsinghua University. And I'd like to introduce our work, the IDEA-GP, an instruction-driven architecture with efficient online workload allocation for geometry perception. And at the beginning, I'd like to share with you about our motivation. There's a very interesting phenomenon in nature called the insect paradox. It states that while the insect accounts for the largest number of the biological species, the proportion size of each individual species is very small. And when we look at the robot technology, the robot chip design faces similar challenges. With the development of intelligent computing, neural network-based algorithms like this account for the majority of applications, while the remaining operators are diverse but only make up a small fraction. This makes it difficult to offset the cost of specialized chip design through mass production. However, these applications are still very important. So this leads us to think about how to design a more general architecture beyond these intelligent algorithms. And there's always a big problem between the conflict of the dedicated architecture and the general architecture. On the one hand, the dedicated architecture work well for specified tasks, but often failed when we meet variant algorithms or new operators. On the other hand, the general architecture while trying to support a wide range of operators, they tend to waste a lot of computing resource, which reduce their overall processing efficiency. Also, when a scenario or task changes, the demand and workload on different operators will change as well. This makes it hard to balance the efficiency and generality. So the key, we think, is to select the right application domain or to extract the suitable operators. Then we talk about what domain we choose. We think the geometry perception, or we can say the visual perception of the robots, is a great domain. We know that a robot can interact with worlds through a closed loop of perception, planning, and control. And as the intelligent algorithm advance, the neural network can work well on the planning and the control. For example, the reinforcement learning can enable robots to dance around, and the large model-based methods such as VLA, they can help robots to perform a lot of operations like grasping, picking up, and placing things. However, in perception, where high accuracy is required, the traditional methods are still very important. The SLAM and SFM-based method can be used for more accurate localization and more detailed mapping. And they can also be used as a part of another tasks, like the SFM can become the front end of the 3D Gaussian splatting. Moreover, with the increasing use of cameras, visual data become a very important source of our information, and they are very low cost. This also brings a large amount of computation, which highlights the importance of accelerators. So why don't we develop a general accelerator for the robot's visual perception? And we will talk about the challenges. Actually, there are already a lot of works on accelerators of SFM or visual SLAM, and they give us plenty of inspiration. For example, some dedicated accelerators like PyBA and HTest did a great job on speed up the SFM or the SLAM, but their fixed architecture make it hard to adapt to another algorithm. There are also some general architectures like Oriana, which can theoretically handle all of the factor graph-based optimization, including planning, localization, and control. But they don't utilize the sparsity of the visual data. And all of this solution requires to regenerate the architecture when facing different tasks. So we think the key point is how to achieve efficient and online architecture when facing different tasks and scenarios. The online here means we don't need to regenerate our architecture when facing different tasks, and the efficient means most of the computing units can be reused and not wasted. The main challenge here is how to handle the computation flow between different tasks. In fact, the visual perception task follows a similar framework. They gather all of the data from the sensor and to form an optimization problem. And by solving this problem, we can get the best pose estimation. Most of the computation occurs in two main areas. First, to construct this optimization problem, we need to calculate a lot of cost function, which we'll call as the residues in the robot algorithms. And then at the same time, the partial derivative matrix called Jacobi matrix will be calculated at the same time. We call this part as the front end of the optimization. The front end here is a little bit from the usual we talk about the front end. Second, after we get the residues and the Jacobians, we need to solve a sparse equation to get the updates of our pose estimation. And with a lot of iteration, finally, we get the best estimation of our pose. And we call this part as the back end of the optimization. So challenges when dealing with different tasks, the front end and the back end have different kinds of computation flow. So first, in the front end, the different optimization methods are made up of different kinds of residues. And even when we're dealing with the same type of data, such as visual data, we have different form of the residues too. And moreover, the computation of the Jacobi matrix will also changes when facing different kinds of the variables. And in the backend, different residues can lead to different sparsity patterns. This also changes the computation flow. Additionally, these variables in the computation flow can result in some changes to the overall system workload, which means that the front end and the back end, we have different kinds of workload. So we'll talk about method. To solve this problem and unify this computation flow, we need to know which operators are the most critical in these algorithms. Our answer is that the pose transmission is the most important operators. It's a very important operator in robots. We can regard the robots as a combination of various modules, such as we have different sensors, we have different chairs, and we have different mechanical structures. Through the pose transmission, we can easily describe the relationship between these modules. And by getting the pose transmission relationship between different frames, we can also identify the change in observation of different frames. These changes constitute the residues we call. The pose transmission is performed by left multiplying rotation matrix and adding translation components. Although it's widely used as a fundamental operator in robot algorithms, it's rarely treated as a basic operation in design of computer architecture. It's evident that the calculation of the residues can be done through combining this pose transmission. And it can prove that the calculation of the Jacobi matrix can also be done in this way. As shown right, the table lists the operators we needed. Based on this set of basic operator, we design our processing elements. It consists of a small historical array and is capable of performing nearly all the operators we mentioned before. By using some simple control signals, we can control which computation mode it should be applied to the current data. Using a group of P's, we can easily achieve the calculation of different residues and Jacobians. The raw data just flow between these P's, and we apply different control signals on them to get final results. For backend, it's a little bit more complex, which utilize the characteristic of the pose vector. Since the pose will be always represented by a 3D or 6D vectors. The Jacobian matrix have a fixed structure of its non-zero elements in the direction of row. So they just appeared in the group of 3, and by processing the matrix row by row, we can use these small submatrix operators to perform the big matrix elimination. These operators are the same as the operator we use in the front end. So it means that we can use the same PE to do both the solving of front end and back end. You can find some details of the elimination steps in our paper. But in summary, we finally obtain a dense matrix, and this matrix solving by the CPU. And we design a instruction set for the scheduling. To handle the challenge of workload balance across different tasks and scenarios, our each instruction includes a parameter called PI, which specify the PE controls. In this way, we can conduct the PE to perform either front-end computation or the back-end calculation. Thereby, we can achieve the workload allocation. Of course, this fine-graded scheduling at PE level can bring considerable pressure on the bandwidth. So we also design some high-level instructions based on the characteristic of the elimination method itself. By configuring the parameters of these high-level instructions, they can be broken down into some small instructions on chip. Thereby, we can reduce the bandwidth pressure. And finally, we come to the results. We also design a compiler implemented in C++ and deployed on the CPU. The compiler mainly accomplishes 3 tasks. First, re-render the raw data and store it in the DDR in a write form for easy use by the accelerator. Second, it estimates the workload of front end and back end, and then it allocates the number of PE for each. Third, it generates some instructions based on the PE allocation to control our accelerator. And then we come to the results. This table shows the sets of our experiments on hardware, algorithm, and data sets. First, we conduct some experiments on the workload of a system. The figure above shows that the workload proportion of front and back end will change between different algorithms. And the figure below shows that by allocating PEs, we can achieve the minimum computation time. We also analyze the instruction bandwidth. Through the design of high-level instructions, the instruction bandwidth only accounts for a small fraction of overall bandwidth, which is less than 5%. This means that using instruction for scheduling is highly efficient. In terms of computing speed, we'll compare our results with ARM and Intel CPU, and we can observe the significant speed up in both LAM and SF10 tests. We didn't compare with a GPU because the previous work has proved that due to the sparsity of data, GPU can hardly provide any additional acceleration. Given the difficulty in directly comparing with other accelerators, I will make some qualitatively comparison with the previous work. So in conclusion, by enabling online configuration of accelerators through instruction-driven approach, Ideal GP offers 2 key benefits. First, it can switch smoothly between different algorithms without needing regeneration. And second, its online resource and workload allocation ensure the optimal computation speed for each algorithm and scenarios. And since we don't have to change the hardware, the ASIC improvements become a real possibility. And that's all. Thank you.